Okay, let's jump straight into a deep dive into the absolutely fascinating source material you sent in.
Sound great.
Today, we're exploring the incredible intersection of, well, artificial intelligence and space
A
exploration.
really hot topic right now.
Totally. When you think about the sheer scale of the universe, I mean, the billions and billions of stars, it's easy to feel overwhelmed.
Hmm.
Finding planets way, way beyond our solar system, these incredible places we call exoplanets, it just feels like searching for a single grain of sand on every beach on Earth all at
The
once.
mind-boggling analogy, but yeah, pretty accurate.
And missions like Kepler and TESS have just, compounded that feeling. They gave us this avalanche of data from monitoring hundreds of thousands of stars for years.
An absolute data deluge.
So trying to sift through all of that for the tiny, tiny subtle signals of distant worlds, it truly is the ultimate needle in a haystack problem, isn't it?
And you hit on exactly why AI has moved from being like an interesting tool to being an absolutely fundamental necessity in this field.
Right.
It's not just about helping us find those needles in the astronomical haystack. The sources you provided make it crystal clear that AI is fundamentally transforming almost every aspect of how we approach space exploration right now, and definitely looking into the future.
In what ways specifically?
Well, we're talking about its impact on the telescopes, actually collecting the data, the way we operate missions, even the futuristic colonies we might one day build, and the probes we dream of sending to other stars. It's everywhere.
That's what makes these sources so compelling, I think. They really show how AI is making these seemingly impossible possible, drastically accelerating our pace of discovery and capability in space.
Accelerating is the key word.
So our mission for this deep dive is to really unpack this transformation. We'll start by looking at how AI is actively finding exoplanets right now.
The current state of play.
Exactly. Then explore the specific AI techniques that are making this happen, then kind of see how AI is being integrated into the very fabric of space technology, both current and future stuff.
From the ground analysis up to the spacecraft themselves.
Right. And finally, we'll zoom out and ponder the truly profound implications of using artificial intelligence in the search for life beyond Earth and, what it means for humanity's future among the stars.
Big questions.
Yeah, totally.
And again, just to reiterate, this deep dive is built entirely from the materials you shared with us, giving you a unique shortcut to understanding this cutting-edge field directly through the insights you've curated.
Perfect. So let's begin with the most immediate, tangible impact we see in the sources, how AI is actively finding exoplanets now.
Okay.
And a huge part of this story is simply grappling with the sheer volume of data, particularly from missions using the transit method.
That's really the cornerstone for missions like Kepler and TESS. The transit method, it's conceptually pretty simple, right?
Yeah, seems straightforward.
You observe a star, you wait, and you look for a tiny periodic dip in its brightness. This dip happens when a planet passes directly in front of the star from our point of view, blocking just a little bit of its light.
Like watching a distant car headlight dim momentarily as a tiny fly crosses in front of it.
That's a good analogy, yeah. It's a tiny effect.
But as you said, Kepler and TESS aren't looking at just one light bulb. They're monitoring hundreds of thousands, maybe even millions, simultaneously for years on end.
Yeah, Kepler gave us a decade of observations for just one patch of sky. And TESS is doing something similar, but for pretty much the entire sky over time.
Wow.
We're talking about generating terabytes upon terabytes of data. These huge archives of light curves, which are basically just graphs tracking how bright each star is over time.
Mountains of graphs.
Mountains. And within that massive data set, you're looking for incredibly subtle dips. I mean, for an Earth-sized planet crossing a sun-like star, the dip might be less than 1% of the star's brightness.
Tiny.
And it's not clean data either, right?
Yeah.
Oh, not at all. That's the kicker. Those tiny signals are buried in noise. You've got flickering from the star itself, like star spots and flares, maybe light bleeding over from background stars, and even, quirks and wobbles from the telescope instruments themselves.
So it's messy.
Very messy. For human eyes, or even traditional software designed to look for simple patterns, spotting these tiny, infrequent dips across terabytes of noisy data is incredibly time-consuming. And frankly, you miss things. It's prone to error.
Which is where AI steps in.
Exactly. This is precisely why AI has become so crucial. A machine learning algorithm can tirelessly analyze vastly more data, much, much faster, and often with greater precision in picking out those subtle, noisy signals compared to human analysts or classical statistical methods.
So AI becomes this relentless, super efficient data sifter. the planet spotter.
You got it.
And the sources highlight some early successes where AI really proved its worth in this transit data, right?
Absolutely. Back in the 2010s, when the Kepler mission was really churning out its initial results, researchers started applying neural networks to the data. A landmark example, often cited in the sources, is the work done by Google AI.
Google, what did they do?
They trained a deep learning model specifically on the Kepler light, curves those patterns of star brightness over time. They basically taught the AI what a planet transit should look like, even amidst the noise.
And what did that system find? Anything new?
That's what was so remarkable. It went back through existing Kepler data, stuff that had already been analyzed, and it discovered additional planets that had been previously missed by the human or traditional automated analysis pipeline.
Seriously? Missed planets?
Yeah, most famously, it discovered Kepler 90I. This discovery completed the Kepler 90 system, making it the first known 8-planet system found outside our own solar system.
Whoa, okay, that was a huge moment. Finding another 8-planet system that really demonstrates AI could find signals hidden even after all that human effort.
Exactly. It wasn't just, a cool academic exercise. It was a clear, practical demonstration that deep learning could actually outperform the established manual and traditional automated techniques in recognizing these complex, subtle dimming patterns that indicate a planet.
And it wasn't just a one-off.
Not at all. That success really cemented AI's place. Modern exoplanet hunting pipelines for the later Kepler data, the key to mission phase, and definitely for the ongoing TESS mission, now routinely incorporate AI as a core component.
And the sources specifically call out Exoplanet as a key player in this now. What's that?
Yeah, Exoplanet is a really prominent example. It's a deep neural network developed through a collaboration between NASA and the SETI Institute. Its power lies in how it was trained.
How so?
It was rigorously trained on light curve patterns from thousands of confirmed planets, so it learned what real transits look like. But crucially, it was also trained on patterns from thousands of known false positives.
False positives, like things that look like a planet transit but aren't.
Exactly that. The most common ones are things like eclipsing binary stars, where one star passes in front of another from our view, which can mimic a planet's dimming. Or it could just be instrumental noise artifacts or other weird astrophysical phenomena. Exoplanet learned to distinguish the true planetary dip signature from all these imposters.
Okay, so the AI became this really sophisticated filter, specifically trained to separate the wheat from the chaff in transit signals. That's clever.
Precisely. And its impact has been pretty significant. In 2021, Exoplanet was used to validate over 300 exoplanets in the Kepler dataset that were previously just candidates.
300 validated planets, just like that.
Well, validated by the AI's analysis, yeah. And more recently, in 2023, an improved version, Exoplanet V1.2, confirmed an additional 69 exoplanets that were still lingering as candidates needing validation.
Wow. And the sources mentioned something neat about V1.2, a multiplicity boost.
Yeah, that's a cool feature. If a star already had one or more known planets confirmed orbiting it, the AI could use that information. The fact that it's already known to be a planetary system to increase its confidence when evaluating other, perhaps weaker, potential transit signals around that same star.
That makes intuitive sense.
Yeah.
If you already know there are planets there, another tiny dip is maybe more likely to be another planet than just random noise.
Right. It adds a bit of prior probability.
Mhm.
And this whole AI-driven validation process is incredibly valuable because it really accelerates the confirmation of exoplanet candidates.
How does it accelerate things?
Well, traditionally, confirming a candidate requires extensive follow-up observations, usually using ground-based telescopes, to rule out false positives or get more data.
Yeah.
That's a huge bottleneck because telescope time is limited and precious. AI validation, like with Exoplanet, can provide a very high degree of confidence based just on the space telescope data, sometimes bypassing the need for some of those time-consuming ground observations. It significantly speeds up the rate at which we move from candidate to confirmed planet.
And the sources mentioned a visualization related to this?
Yeah, they described a chart showing exoplanet radius versus orbital period. It visually highlighted how Exoplanet V1.2 validated dozens of these previously stuck candidates across a whole range of sizes and orbits planets that were just sitting in the Kepler test data, needing that extra AI scrutiny to push them over the line to confirm status. It even showed Earth's position for context.
The sheer numbers AI is contributing here are just impressive.
They really are. As of early 2024, we're over 500 to 600 confirmed exoplanets in the official catalog. The vast majority came from transit surveys like Kepler and TESS, And a really significant percentage of those were either initially identified or, like we just discussed, validated using machine learning techniques.
And that trend is only going up.
Absolutely expected to grow. AI is essentially acting as this tireless, hyper-efficient research assistant. It sifts through astronomical quantities of data, day in and day out, flagging the most promising candidates for human astronomers to then focus their precious time and expertise on.
But the sources make it clear AI isn't just a one-trick pony for the transit method. It's boosting other detection techniques too.
Oh, definitely. It's impacting pretty much all the major methods. Let's talk about the radial velocity method.
Right, that's the wobble one, right?
Exactly. This technique involves detecting tiny, tiny wobbles in a star's motion, caused by the gravitational tug of an orbiting planet. You detect it by looking for subtle shifts in the star's spectrum, its light signature due to the Doppler effect as it moves slightly towards and away from us.
I imagine separating the planet's tiny tug from the star's own activity, things like star spots or flares, must be incredibly challenging. That sounds like inherently noisy data.
Precisely. That's the main difficulty. Stellar activity, the star's own jitteriness, introduces significant noise that can easily mimic or completely hide a small planet's signal.
So AI helps untangle that.
That's the goal. The source mentions a system called Exoplanet. It's a deep learning algorithm specifically developed to analyze these radial velocity time series data and distinguish the genuine periodic planetary wobble from the more chaotic stellar noise.
How do they train it for that?
Critically, it was trained on simulated data. They created artificial planet signals and injected them into datasets containing realistic stellar noise patterns. This teaches the AI how to ignore the star's own complicated behavior and focus on the planet's signature.
And how did this AI perform in testing? Did it work well?
The results, although tested on simulated datasets so far, were very promising according to the sources. Exoplanet achieved 28% fewer false positives compared to traditional statistical methods used for RV analysis. And, get this, it was astonishingly 5 orders of magnitude faster in processing the data.
Wait, 5 orders of magnitude faster? That's like saying it can analyze in seconds what used to take days or weeks.
Exactly. It shows the potential for dramatically speeding up the analysis pipeline. And the source specifically notes that this improvement was most pronounced for the really small, weak signals produced by low-mass planets, precisely the kind that are often buried deep in the noise and missed by classical approaches.
So it could make us more sensitive.
That's the hope. It suggests neural nets like Exoplanet could significantly increase our sensitivity in radial velocity surveys, potentially allowing us to detect Earth-mass planets in the habitable zones of their stars, even when the signal is incredibly faint and noisy.
So AI isn't just automating existing methods, it's potentially making them more powerful, letting us find smaller, harder to detect planets. What about trying to take actual pictures of planets' direct imaging?
Direct imaging. That's notoriously difficult. A planet's own light is millions or even billions of times fainter than the light of its host star. It's like trying to spot a firefly next to a searchlight.
Yeah, sounds impossible.
Extremely challenging. But AI is being employed here too, mainly to enhance the very complex signal processing techniques needed in high-contrast imaging and spectroscopy. These are methods designed to block out the overwhelming starlight and analyze the planet's faint glow.
How does AI help with that?
Machine learning algorithms are proving effective at things like subtracting the residual starlight more cleanly, reducing noise, and critically, isolating the planet's unique spectral signature, its molecular fingerprints, from the remaining noise. This isn't just about detecting the planet, but potentially understanding its atmosphere.
Okay, so the AI helps dig out the planet's tiny signal from the star's blinding glare and the messy leftovers.
That's the core idea, yes. And even in gravitational microlensing.
That's the one where gravity bends light, right?
Exactly.
Yeah.
A foreground star's gravity can act like a lens, bending and magnifying the light of a distant background star, causing a temporary brightening event. If there's a planet orbiting that foreground lensing star, its own smaller gravity can cause a brief secondary blip or distortion in that brightening event.
Sounds rare and quick.
Very rare, and the planetary signal is often very short-lived. These events are buried in massive datasets from sky surveys looking for any kind of variable object. The sources mention that random forest classifiers, another type of AI, are being used to automatically identify these fleeting microlensing events in the survey data, effectively separating them from the much more common noise of regular variable stars.
So it seems like across the board, whether it's a dip, a wobble, a faint glow, or a flicker, AI's core strength in recognizing complex patterns hidden within noisy datasets is proving transformative for every major exoplanet detection method.
Absolutely. That's the common thread. AI excels at sifting through messy, complex data to find the specific type of signal you're looking for, regardless of the underlying physical effect causing it.
And it doesn't stop at just finding the planets, right? The sources show it's also crucial for understanding them once they are found.
Correct. AI's role extends significantly into the data analysis and characterization of exoplanets. One of the most exciting applications here is in analyzing the faint light that filters through an exoplanet's atmosphere during a transit, or the light reflected from its surface or clouds.
To figure out what the atmosphere is made of.
Exactly, and maybe even infer things about its potential habitability. Scientists are training machine learning models on synthetic spectra, basically, simulated light profiles of what Earth-like planets or other potentially habitable worlds might look like if they had different atmospheric gases, surface features like oceans or continents, or maybe even signs of biology.
Signs of biology, like
Yeah,
vegetation. Looking for signs of plant life on a distant world using AI, that sounds incredible.
it is, and it's a concrete example highlighted in the sources. There was a 2020 study where they trained an AI specifically to recognize the spectral red edge.
What's the red edge?
It's a distinctive pattern in the light spectrum where plants on Earth strongly reflect certain wavelengths of near-infrared light. It makes vegetation look bright in infrared photos. The AI was trained on simulated planetary reflectance data, what light bouncing off different simulated planet surfaces might look like. And it could correctly detect the simulated presence of a biosignature analogous to Earth's red edge about 75% of the time in their tests.
Whoa, so it's not saying they found alien plants, obviously, but it's a powerful proof of concept showing that AI could potentially spot that kind of signature if it were actually there in data from future, more powerful telescopes like JWST or upcoming observatories.
Exactly. It's a tantalizing demonstration of AI's potential for identifying worlds that are potentially life-friendly or exhibit what might be biosignatures. Now, these algorithms often provide probabilistic clues. They might say, there's an X% chance certain gases are present or estimate a percentage of the surface covered by something lifelike based on the spectrum.
So not definitive proof on their own.
No, but they are incredibly valuable. They allow scientists to quickly analyze incredibly complex spectral data that would be almost impossible to interpret fully by eye, and crucially, they highlight the most promising candidates that warrant more intensive follow-up observations with our most powerful telescopes. It drastically speeds up the search for truly compelling targets.
Okay, so to kind of synthesize AI's current role in exoplanet science based on these sources, it seems like it's really integrated throughout the entire pipeline from start to finish.
It absolutely is, right from the initial filtering and reduction of those massive raw data sets coming down from the telescopes, through the identification of potential planetary candidates, distinguishing the true signals from the false alarms.
Like Examiner does.
Right. Then validating those candidates with increased confidence, and even helping to characterize the properties of the planets once they're found by analyzing their light for atmospheric composition or other features. AI automates the incredibly tedious and complex analytical tasks that would simply be impossible for humans to do at the scale required by current and future data volumes.
Leaving the astronomers to focus on the interesting stuff.
Exactly. It frees astronomers to apply their expertise and intuition to the most interesting and compelling targets that the AI flags up. As the datasets from missions like TESS and soon others like Plato or the Roman Space Telescope continue to grow exponentially, these AI techniques are becoming less of a helpful add-on and more of an absolute necessity for making progress in the field.
It's truly revolutionizing the search itself. Okay, let's maybe delve a bit into the specific types of AI that are being used here. The sources refer to exoplanet signal identification fundamentally as a pattern recognition problem, which makes sense, and that makes it ideal for machine learning.
That's the core principle, yeah. These subtle signals, the dips in light, the stellar wobbles, the spectral features, they're all distinct patterns, but they're embedded within a whole lot of noise and other confounding signals from the star or the instrument. Machine learning algorithms are specifically designed to find and classify exactly those kinds of complex patterns.
And the sources give us a glimpse into the key techniques in this AI toolkit astronomers are using. Let's maybe start with deep neural networks, DNNs.
Okay, deep neural networks, or DNNs, they're really a cornerstone of modern AI. They're excellent at general pattern recognition and classification tasks. In exoplanet hunting, they're trained on vast amounts of data, examples of transits, examples of noise, examples of false positives, to learn how to classify any new input signal as either likely planet or likely not planet.
How do they work, roughly?
They use multiple layers of interconnected artificial neurons. Each layer progressively extracts more complex and abstract features from the raw data. Examiner, which we already talked about, is a prime example of a DNN successfully learning to differentiate the subtle shape of a true transit from various types of false positives. The Google AI system that found Kepler 90I also relied heavily on DNNs trained on those light curve shapes.
Okay, so DNNs are like the general purpose pattern classifiers here. What about convolutional neural networks, CNNs? They sound related, but maybe more specific.
They are related, yeah. CNNs are a specialized type of neural network that are particularly adept at processing data with a grid-like structure, like images or sequential data, like time series.
Like light curves.
Exactly. Light curves from transit surveys are perfect for CNNs. They use special layers with filters that effectively scan over the time series data, automatically learning to pick out specific local shapes or features, like the characteristic U or V shape of a transit dip, regardless of exactly when or where it occurs in the long light curve.
So they're good at finding the shape.
Very good. The AstroNet system, which was also developed by Google and NASA for analyzing Kepler data, was primarily a CNN. They're also proving effective in radial velocity analysis for distinguishing the relatively smooth, periodic signal of a planet's gravitational tug from the more complex, almost fractal-like patterns caused by stellar activity noise.
Okay, so CNNs are great at specifically identifying the shape of the signal over time, or maybe in a spectrum. What about ensemble methods? The sources mention things like random forests or boosted trees.
Right, ensemble methods, these are supervised learning techniques, but instead of relying on a single complex model, they combine the outputs of multiple simpler models, usually decision trees.
Like polling a committee of experts.
That's a perfect analogy. Each individual decision tree makes a classification based on a series of simple questions about the data features, like, is the transit duration consistent with a planet of this star's size? What's the signal-to-noise ratio? An ensemble method like random forest builds many such trees, each trained on slightly different subsets of the data or features, and then combines their votes, maybe by simple majority or a weighted average, to produce a final classification that's typically more robust and reliable than any single tree alone.
Why is that better?
It reduces the risk of overfitting to noise in the training data and generally leads to better performance. They're also good for handling structured data, and some ensemble methods can even provide insights into which features of the signal were most important for making the classification decision. The source mentions random forest classifiers being used effectively to automatically detect those fleeting gravitational microlensing events by distinguishing their unique light curve shapes from other types of variable light sources. Studies have shown ensembles can achieve very high accuracy, often over 90%, in classifying exoplanet candidates from transit surveys.
Okay, so getting a consensus from multiple experts built into the algorithm increases confidence. Interesting. What about Bayesian methods and Gaussian processes? These sound a bit more statistical, less like pure pattern matching.
They're powerful statistical tools, and they're often used in conjunction with, or sometimes as an alternative to, machine learning classifiers. Gaussian processes, or GPs, are particularly useful in exoplanet science for modeling noise, especially complex correlated noise like the variability caused by stellar activity in radial velocity data.
How does modeling the noise help?
Well, if you can build an accurate statistical model of what the noise looks like, how it behaves over time, you can then effectively subtract that noise model from the observed data, hopefully revealing the often tiny planetary signal hidden underneath. GPs are very flexible for this.
Got it. And Bayesian methods.
Bayesian methods provide a framework for reasoning about probabilities and updating beliefs based on evidence. In exoplanets, a tool like Vespa, which was referenced in the sources, uses Bayesian statistics to calculate the probability that a given transit candidate signal is actually a false positive, based on various characteristics of the signal and the star. This provides a quantitative measure of confidence that complements the classification output from machine learning models. And increasingly, machine learning techniques are actually being used to help optimize the parameters within these statistical models, like GPs, making them faster and more effective at finding weak signals.
So GPs help clean up the data by modeling noise, and Bayesian methods help assess the statistical likelihood that what's left is a real discovery versus a fluke. Makes sense. But what about finding things you weren't specifically looking for? Unexpected stuff.
That falls into the realm of unsupervised learning. Techniques like clustering or anomaly detection are key here. Unlike the supervised methods we've been discussing, These algorithms don't require labeled training data where you've already told the machine this is a planet or this is a false positive.
So they find patterns on their own.
Exactly. Clustering algorithms, like the common k-means algorithm, can take a large dataset of known exoplanets, perhaps described by their size, mass, orbital period, and temperature, and automatically group them based on their similarities. This can reveal natural groupings or classes of planets distinguishing, say, hot Jupiters from super-Earths or cold gas giants. Or, maybe more interestingly, it can highlight outliers, a planet that doesn't fit neatly into any of the established groups, perhaps indicating something unusual about its formation or properties that warrants further investigation.
And anomaly detection.
Anomaly detection algorithms, often using techniques like autoencoders, are specifically designed to flag data points or patterns that are significantly different from the vast majority of the data.
Like a light curve with a really bizarre shape that isn't a standard transit dip or a known type of stellar flare.
Precisely. It could just be a weird instrumental artifact, sure, but it could also be a sign of something genuinely new and exciting. Maybe an unusual type of stellar behavior, a planet with strange rings or moons causing an odd transit shape, or even a misclassified exotic object. Unsupervised learning helps astronomers spot these unknown unknowns, strange signals that might otherwise be completely overlooked if they were only searching for predefined patterns they already expected to find.
Very cool. And finally, reinforcement learning, or RL. The sources list this, though it seems maybe less directly about finding the planets themselves.
That's generally true. RL is a different beast. It's a type of machine learning where an agent learns to make a sequence of decisions by interacting with an environment, aiming to maximize some kind of cumulative reward signal, while not typically used for identifying the planet signals directly in the data. RL is finding applications in areas like optimizing observation strategies or operating telescopes autonomously. The sources mention recent research into self-driving telescopes, which uses RL to teach an AI agent how to autonomously schedule observations for a telescope network.
So the AI learns how to be the most efficient scheduler to get the best science.
Precisely. The reward in this case might be maximizing the amount of high-quality data collected or maximizing the number of scientifically valuable targets observed under good conditions. While still mostly in the simulation and testing phase, one study mentioned used a deep Q network, a type of RL, and achieved around 87% of the theoretical optimal efficiency in scheduling observations for a small simulated observatory. This shows RL's potential to optimize the entire exoplanet search process, perhaps deciding which newly detected candidates are most promising to prioritize for follow-up observations based on the learned likelihood of them being real planets.
It's really clear this isn't just one single type of AI doing all the work. It's a whole sophisticated toolbox. And the sources emphasize how these techniques often work together in practice.
That's absolutely key. A modern exoplanet search pipeline is rarely just a single algorithm working in isolation. As described in the sources, a typical workflow might involve several stages. Maybe a fast CNN scans the raw light curves first to identify potential features of interest.
The first pass.
Right. Those candidates are then passed to a more sophisticated classifier, like a random forest or a boosted tree ensemble, which uses additional information about the signal shape, the star's properties, etc., to calculate a probability of it being a real planet. Simultaneously, perhaps Gaussian processes are being applied to carefully model and remove the stellar noise from the light curve or radial velocity data before classification. Then, maybe Bayesian methods are used to calculate the statistical false positive probability for the remaining candidates. Results from multiple different AI algorithms might be compared and cross-checked. And finally, human scientists carefully examine the candidates that manage to pass through all these automated AI filters.
Okay, so the AI rapidly narrows down the overwhelming possibilities, doing the heavy lifting of screening, leaving the scientists to apply their judgment and plan follow-up observations on the most promising few.
Exactly. The AI handles the massive data screening challenge, and the irreplaceable human expertise is focused where it matters most, on the most compelling, complex, or potentially groundbreaking cases. And underlying all of this, something the sources really stress, is the critical importance of robust training for these AI models.
Right. The idea that AI models are only as good as the data they learn from, and the need to avoid pitfalls like overfitting or bias.
Absolutely crucial. If an AI model is poorly trained or trained on biased data, it might learn spurious correlations patterns that exist by chance in the training data, but aren't real physical signals. It might become really good at recognizing features specific to the training set, but fail miserably when applied to new, unseen data. To ensure the findings are reliable and scientifically valid, AI models used in astronomy are developed and tested with extreme care and rigor.
Can you give us some specific examples of that training rigor that came up in the sources?
Certainly, Examiner, for instance. It was trained on tens of thousands of carefully labeled examples from the Kepler mission, both confirmed transit signals and meticulously cataloged examples of known false positives. But the crucial part, as the sources highlighted, was that its performance was validated on new transit events for different parts of the Kepler data that it had not seen during its initial training phase.
Why is that testing on new data so important?
It prevents the AI from simply memorizing the training data, a problem called overfitting. By testing it on completely new examples, you ensure it has actually learned the underlying generalizable features that differentiate a real planet signal from noise or a false positive, and isn't just regurgitating patterns it saw before. It proves the model can generalize its knowledge.
That makes perfect sense. You test it on a final exam with new questions, not just the homework problems it already did.
Precisely. Similarly, the exoplanet algorithm for radial velocity analysis, remember, the one designed to separate planet wobbles from stellar noise.
Oh,
It was trained on synthetic radial velocity datasets.
synthetic, not real data.
They created simulated planet signals with known properties and deliberately injected them into real stellar noise data taken from observations of stars without known planets.
Yeah.
This forced the neural network to learn the generic signature of a planet's gravitational tug, independent of the specific noise characteristics of one particular star or one particular telescope's instruments. This makes the trained model more robust and likely to work on data from different stars and instruments.
Oh, okay, that's clever too. Teach it the signal, not the quirks of the noise source. Why does all this meticulous training and validation process matter so much for exoplanet discovery specifically?
Because the stakes can be very high, scientifically speaking. Each potential exoplanet discovery, especially one that might hint at being in the habitable zone or having interesting characteristics, is significant. You absolutely need to have high confidence in your results before announcing them or dedicating precious follow-up resources. False positives can waste enormous amounts of valuable telescope time and scientific effort. Trust in the AI's output has to be earned through this kind of rigorous, transparent testing and validation process.
It's not just about having AI, it's about having reliable, scientifically validated AI that you can trust.
Exactly. And the synergy created by combining these different AI approaches, maybe a CNN for initial feature detection, an ensemble method for robust classification, GPS for careful noise modeling, is really pushing the boundaries. It's allowing astronomers to dig deeper into the noise, to look for even smaller planets or planets around noisier stars, signals that were previously inaccessible. And importantly, these techniques aren't developed in a vacuum. They're being applied and adapted across many fields of astronomy for classifying galaxies, finding supernovae, analyzing cosmic microwave background data. AI is rapidly becoming a truly ubiquitous and indispensable tool in the modern astronomer's toolbox.
Okay, so we've seen how AI is absolutely essential for finding and analyzing exoplanets from our vantage point here on Earth or from near-Earth-based telescopes. But the sources then shift focus significantly, talking about integrating AI off-world, putting it directly into spacecraft and mission operations. This feels like a whole different level of application.
It absolutely is. This is moving beyond AI as just a tool for analyzing the data after it comes back from space. It's about increasingly building AI capabilities into the spacecraft themselves and using AI to manage complex missions in real time. This is where things get really exciting, I think, for the future of exploration.
And why is this shift towards onboard AI and autonomy becoming so necessary?
Fundamentally, it comes down to complexity and distance. The complexity of modern space observatories, intricate scientific probes, and especially the planned massive satellite constellations, demands a level of operational autonomy that human operators on the ground simply cannot provide effectively 24/7/10. Managing their intricate schedules, monitoring their health, processing the sheer volume of data they generate, and making rapid decisions, especially for distant missions with significant communication delays, requires machines to take on more decision-making responsibilities autonomously.
Like letting telescopes manage their own observing time. Is that really happening?
Exactly. Autonomous telescope scheduling is a prime example cited in the sources. Observatories, whether in space like Hubble or on the ground, often have multiple science goals, competing requests for observation time from different teams, and constantly changing windows when specific targets are visible or conditions are right. AI planners are ideally suited to tackle this complex, multi-objective scheduling problem, optimizing the sequence of observations to maximize scientific output while respecting all the constraints.
Any examples?
The sources mention systems like Hubble's Spike system, which use rule-based AI techniques even years ago to automatically generate detailed, efficient observation timelines. More recently, that 2023 study we touched on with reinforcement learning showed a deep Q network achieving about 87% of the theoretical optimal efficiency in scheduling observations for a small observatory and simulations. That points towards highly efficient autonomous scheduling.
And for the massive new surveys coming online, like the Rubin Observatory.
Oh, it will be absolutely essential. The Virasey-Rubin Observatory is designed to image the entire visible southern sky every few nights, generating an unprecedented flood of data. AI scheduling will be crucial just to operate it efficiently. Furthermore, the plan is to have near real-time machine learning pipelines automatically scanning its data stream to identify transient events, things like supernovae exploding, asteroids moving, or other sudden changes in the sky almost as they happen. So AI is integrated into both operating the telescope and processing its data on the fly.
Wow. And the sources mentioned putting deep learning capabilities directly on board the satellites as well. That seems like a really big step AI thinking in orbit.
It is a significant step, yeah. The European Space Agency's ASAT-1, VSAT-1 mission launched in 2020 with a landmark example mentioned. It was the first satellite to carry a dedicated deep learning processing chip on board. Its AI was trained for a specific task, analyzing the Earth observation images it took while still in orbit.
What was it analyzing them for?
He was trained to decide whether the images were too cloudy to be scientifically useful.
Seriously? So it could filter out the useless cloudy pictures before sending them back to Earth?
Precisely. Instead of sending back every single image it took and letting ground teams waste time downloading and sorting through potentially gigabytes of useless cloudy data later, the satellite's onboard AI analyzed them in real time. If an image was completely obscured by clouds, it simply wouldn't transmit it back.
That must save a ton of bandwidth and time.
Huge savings in precious communication bandwidth, yes. And it also allows for much faster reaction times for time-sensitive events like natural disasters. If the AI identifies a clear image over a disaster zone, it can flag it for immediate download, getting critical information to responders much quicker. ESA is already planning a follow-up, SAT-2, with even more advanced onboard AI capabilities. And NASA is actively exploring similar concepts for future Earth-observing satellite and even probes going to Mars. Imagine an onboard AI detecting a major volcanic eruption or a significant dust storm on Mars and alerting scientists immediately, rather than waiting potentially days for the data to be downlinked and processed on the ground.
It really feels like shifting the intelligence, or at least some of the processing workload, from the ground station right into the spacecraft itself.
That's exactly the trend. And AI is also being applied to less glamorous but absolutely critical tasks like spacecraft maintenance, health monitoring, and managing the increasingly crowded environment in Earth orbit.
Like keeping satellites healthy automatically.
Yes, monitoring their health. Think about sophisticated robotic systems like the Canadarm2 on the International Space Station. It already uses autonomous routines, a form of AI, to perform delicate and highly precise maneuvers like grappling and docking, visiting cargo vehicles, or performing detailed inspections of the station's exterior. Looking ahead, the sources envision AI-guided servicing satellites that could autonomously rendezvous with defunct satellites or large pieces of space debris to perform repairs, refuel them, or safely deorbit them. These tasks require very precise control and quick reaction times that are difficult, if not impossible, to achieve reliably with manual teleoperation from Earth due to the inherent communication delays.
Makes sense. And you mentioned space traffic management. With all the thousands of satellites going up, that must be getting to be a nightmare.
It's rapidly becoming a significant challenge, yeah. And AI is seen as essential for managing it. Advanced algorithms are needed just to track all the objects, predict potential collisions between the thousands of active satellites in orbit, and the tens of thousands more planned for megaconstellations, and then issue timely warnings or even command autonomous avoidance maneuvers. Researchers at places like MIT have developed AI models that can coordinate the movements of large numbers of satellites simultaneously, calculating collision-free trajectories for entire constellations in mere split seconds. This kind of capability is absolutely necessary to prevent a catastrophic cascading chain reaction of collisions, known as the Kessler syndrome, especially with the advent of these huge satellite networks.
It really sounds like the machines are being entrusted with more and more critical responsibility in space.
They absolutely are. The sources describe this trend as a shift towards human-on-the-loop control, rather than the traditional human-in-the-loop. What that means is engineers on the ground are increasingly setting the high-level goals, defining the operational boundaries, and supervising the overall system, while the AI systems on board or in automated ground systems are handling the routine, complex, and time-sensitive decisions involved in execution.
Why that shift?
It's far more efficient, and in many cases, it's becoming the only practical way to manage the sheer scale, complexity, and speed required for modern and future space operations, especially in deep space or in large dynamic constellations.
Okay, but given the inherent risks in space, things can go wrong very fast. How are agencies like NASA ensuring that this increased autonomy is actually safe and reliable? That must be a huge concern.
A paramount concern, yes. The sources are very clear that agencies like NASA and ESA are proceeding very carefully and deliberately. There are stringent guidelines being developed and applied for certifying autonomous systems for use in space, emphasizing extreme reliability, robust safety protocols, and exhaustive testing and validation in simulations and on test beds before deployment on a real mission.
So, lots of checks and balances.
Absolutely. Principles of responsible AI, which include things like striving for transparency in the AI's decision-making processes where possible, ensuring predictability, and building in robust fail-safe mechanisms, are critical considerations right from the earliest design phases. Autonomous doesn't mean uncontrolled or unpredictable. It means managed by highly sophisticated, thoroughly tested software that can execute complex tasks and respond rapidly within predefined boundaries, essentially embodying human expertise but operating with machine speed and endurance.
So it's more about careful delegation of specific, well-understood tasks to the AI, not just letting the AI completely figure things out on its own without constraints.
Exactly. It's about entrusting well-defined, rigorously tested capabilities to the AI where it offers a clear advantage in speed, efficiency, or safety. And this philosophy extends beyond just routine operations into areas like high-level mission planning and spacecraft autonomy. AI tools are increasingly assisting human mission planners, or in some cases even taking the lead, on incredibly complex tasks like designing detailed mission timelines from start to finish, scheduling sequences of activities for probes or rovers, and optimally allocating limited resources like power, data storage, and fuel over the course of a mission.
Like figuring out everything a rover on Mars needs to do in a typical day automatically.
Yes, exactly that kind of thing. NASA's Jet Propulsion Laboratory, JPL, developed a system called ACEPIN, which is an AI-based planning and scheduling tool. It's designed to take high-level goals provided by scientists, for example, drive to that interesting-looking crater rim and then analyze the rocks you find there and automatically break them down into detailed sequences of low-level commands for the spacecraft or rover.
And it optimizes the plan.
Yes, it optimizes the plan based on a whole host of complex constraints. Things like when the communication windows with Earth are available, how much power the rover expects to have at different times of day, instrument cooldown requirements, avoiding driving during the coldest parts of the night, and so on. ACEPIN has been used to help plan operations for Earth orbiting missions and was even tested successfully as an onboard experiment on the Deep Space One probe many years ago, demonstrating the concept.
And this kind of AI planning is actively being used on current rovers like Perseverance.
Yes, absolutely. The Mars 2020 Perseverance rover carries a sophisticated onboard planning system based on these principles. This allows it to make some of its own decisions about what science observations to perform after it arrives at a new location without having to wait for ground control on Earth to analyze the downlink data and send back a full, detailed plan for every single Martian day.
How does that work in practice?
Combined with its autonomous navigation capabilities, which we'll talk more about, it can proactively select promising science targets it sees nearby and schedule tasks like taking extra high-resolution images, using its laser spectrometer on a rock, or taking atmospheric measurements, as long as those tasks fit within the predefined rules, priorities, and resource constraints set by the science team back on Earth.
That's a significant step up from previous Mars rovers, right? I remember hearing they needed detailed instructions from Earth for almost every move they made and every picture they took.
It truly is a major advance in autonomy. And this AI planning capability is becoming even more sophisticated, enabling coordination among multiple spacecraft or robots operating together. Stephen Cheen, who's a leading AI researcher at JPL, notes in the sources that in 2025, a cadre of Iconos rovers, meaning a team is scheduled to be sent to the moon, potentially as part of the Artemis program or related efforts, and they will use JPL's advanced multi-agent AI software to coordinate their activities collaboratively.
Whoa, okay, so a whole team of rovers operating together on the moon, managed by an AI.
That's the concept being developed and tested. The AI system would help them divide up tasks efficiently. Maybe one rover scouts ahead, while others perform sample collection or analysis.
Mm.
It would manage their individual routes to avoid interfering with each other or getting into hazardous terrain, and critically, it would allow the team to react dynamically to discoveries in near real time.
How so?
If one rover finds something particularly interesting, like a deposit of water ice, the AI system coordinating the team could immediately redirect other nearby rovers with different instruments to converge on that location and assist with further analysis, all without waiting for the substantial round-trip communication delays between the Moon and Earth. Multi-agent planning and coordination is an area where AI naturally excels, as it can consider far more possibilities and optimize the team's actions much faster than human controllers could manage manually for multiple robots operating simultaneously in a complex environment.
That concept of AI-driven autonomous navigation, especially on planetary surfaces like Mars, is just fascinating. The sources go into quite a bit of detail about systems like Perseverance's AutoNav.
Yeah, this is probably one of the most visible and impactful applications of AI in current planetary exploration. Perseverance's enhanced autonav system is a really powerful AI capability that allows the rover to drive much faster and cover significantly more ground on Mars autonomously than any previous rover could.
How does it work?
It uses sophisticated computer vision and AI algorithms to analyze stereo images of the terrain directly in front of it on the fly, in real time as it drives. Based on this analysis, it identifies safe paths, potential hazards like large rocks or steep slopes, and plots its own route forward, continuously updating as it moves.
That sounds like a huge difference compared to how earlier rovers like Spirit and Opportunity drove. I remember that being described as a painstaking stop-and-go process, always waiting for commands from Earth.
It's a night and day difference. Think about Spirit and Opportunity. They would typically drive maybe a meter or two, then stop, take images, send those images back to Earth, which took time. Human operators on Earth would carefully analyze the images and meticulously plan the next meter or two of driving, then send those commands back to Mars. More delay. It was incredibly slow and inefficient, often limiting them to just a few meters of progress per day.
Right.
Perseverance's AI, using AutoNav, can make those critical driving decisions autonomously in seconds. This enables it to traverse much rougher and more complex terrain safely and cover distances of up to 100 meters or even more in a single autonomous drive sequence, dramatically increasing the pace of exploration.
So the AI is effectively giving the rover a kind of real-time instinct for navigating difficult Martian terrain.
That's a great way to think about it, yeah. AutoNav uses machine vision algorithms trained to detect obstacles like large rocks, sand traps, steep drop-offs, or impassable slopes. It builds a 3D map of the surroundings and can even adjust its planned path mid-drive if it encounters an unexpected hazard that wasn't visible from further back. This real-time decision-making and reaction capability is absolutely crucial on Mars, where that round-trip communication delay of around 20 minutes makes direct remote control or teleoperation completely impossible for driving. The robot needs to be able to react to its immediate environment instantly to avoid getting stuck or damaged.
And the AI isn't just driving the rover, the sources mentioned, it's also helping the rover decide what science to do autonomously. Tell me more about EG.
Yes, that's another key autonomous system highlighted, AGS, which stands for Autonomous Exploration for Gathering Increased Science. It was first deployed successfully on the Opportunity rover later in its mission, and is also used extensively on the Curiosity rover, and presumably Perseverance too.
What does AGS do?
After the rover completes a drive and arrives at a new location, the ADAS system automatically analyzes the images taken by the rover's navigation or science cameras. It uses AI algorithms trained by scientists to identify scientifically interesting targets in the new scene. Maybe a rock with an unusual color, a distinct texture, strange layering, or a mineral composition that stands out. Once it identifies such a target, AGIS can then autonomously command the rover's science instruments, like its laser spectrometer, ChemCam on Curiosity, or its close-up imager, to take detailed measurements of that target.
That's incredible. So the rover can actually seize scientific opportunities on its own, even when the human team on Earth isn't immediately involved in targeting.
Precisely. It allows the rover to conduct valuable science during periods when human operators are not actively planning or commanding it. For example, during the time after the main data downlink to Earth, or before the next command sequence arrives, or even during communication gaps. Yeah. AGS has significantly increased the overall science return of the missions it's been used on. And it's actually credited with making some bonus discoveries by Curiosity, like when it autonomously decided to investigate some interesting-looking meteorites that the human science team hadn't initially noticed or planned to observe in detail.
It's maximizing every single moment the rover has on the surface to do useful science.
That's the goal. It
Yeah.
is. And looking ahead, the sources suggest that future onboard AI systems will become even more sophisticated, prioritizing not just what science to do, but also what data is most important to keep. Steve Chien from JPL gives an example. Imagine a future spacecraft designed to watch for unpredictable, transient events like fast radio bursts from space or volcanic plumes erupting on a distant moon. Instead of just recording absolutely everything its sensors detect and potentially overwhelming the limited onboard data storage or the precious communication bandwidth back to Earth, an onboard AI could analyze the event in real time. It could assess its characteristics, compare it to known phenomena, and make an intelligent decision about whether this specific event is scientifically important enough to save in high resolution and prioritize for transmission back home.
Huh. Like a smart camera automatically deciding which photos in a rapid burst sequence are actually the keepers worth saving.
Exactly that analogy. It uses the limited onboard resources, memory, power, bandwidth, much more wisely, ensuring that the most significant and scientifically valuable observations are the ones that actually make it back to Earth for analysis.
Makes a lot of sense. And beyond the driving and the science targeting, AI also plays a vital role in just keeping the spacecraft healthy and operating smoothly day to day.
Absolutely. Fault detection, diagnostics, and overall operations management are critical applications of AI, especially for long-duration missions far from Earth, where you can't just send up a repair crew. Space is a harsh environment, and components can degrade or fail unexpectedly.
How does AI help with that?
AI helps monitor the complex network of systems onboard a spacecraft and diagnose problems, often before they become critical. Many satellites use anomaly detection algorithms. These algorithms first learn what normal telemetry looks like during routine operations, the typical ranges and correlations between hundreds or thousands of sensor readings like temperatures, voltages, pressure, spin rates, etc.
It learns the baseline heartbeat of the spacecraft.
A good way to put it. Then, if a sensor reading suddenly goes outside its normal learned envelope, or if the relationship between two related sensors changes unexpectedly, the AI flags it as an anomaly.
And that could detect a problem, maybe a slow leak or a failing component in its very early stages, potentially before a human controller looking at scrolling numbers would even notice.
Yes, exactly. The AI can often detect subtle deviations from normal patterns much earlier. Once an anomaly is flagged, the system can alert ground operators, provide diagnostic information, or in some cases even take immediate, pre-programmed corrective actions based on predefined rules to try and stabilize the situation.
What about predicting failures before they happen?
That's another area of active research mentioned, using machine learning for predictive maintenance. By analyzing subtle precursors or trends in the long-term telemetry data from components known to wear out, like reaction wheels used for pointing or batteries, ML models might be able to predict when a component is nearing the end of its life or is likely to fail soon. This could allow mission operators to schedule preventative maintenance, if possible, like on the ISS, adjust how the component is used to extend its life, or switch to backup systems before a critical failure occurs, potentially saving the entire mission.
And AI can assist the human mission controllers on the ground too, not just the spacecraft.
Yes, absolutely. AI-based expert systems are increasingly used in mission control centers to help the human team manage the overwhelming flood of data coming back from multiple complex spacecrafts simultaneously. They can assist ground controllers in diagnosing anomalies by suggesting likely causes based on a built-in knowledge base of past incidents and system behaviors. They can also recommend potential recovery procedures.
Helping them sort through the possibilities faster.
Right. And the sources also mention the concept of beacon mode, which is used for some deep space missions. Here, an onboard AI continuously assesses the overall health status of the spacecraft and simply signals it back to Earth with a very simple beacon tone or code, maybe just green for nominal, yellow for a minor issue being managed, or red for a critical problem requiring immediate attention.
So the ground team doesn't need to constantly monitor every single parameter from every spacecraft.
Exactly. It allows a small ground team to effectively manage a large number of spacecraft concurrently, focusing their attention only on the ones signaling yellow or red without needing constant eyes on for the routine, healthy operations of the green ones. It makes deep space network operations much more scalable and efficient.
So AI handles the routine all clear checks, freeing up the human team to focus on the exceptions and the complex problem solving.
Right. And it's really important to reiterate, as the sources emphasize, that in all these critical mission operations applications, AI is always deployed with very conservative fail-safe mechanisms baked in. If the autonomous system encounters a situation it hasn't been explicitly trained for, or if its own internal confidence metrics fall below a certain threshold, it will typically default to a predefined safe, minimal risk state, a safe mode, or explicitly request intervention or guidance from ground control. It's always a layered approach. AI provides speed, efficiency, and vigilance for routine and well-understood situations, but human oversight and judgment remain the ultimate authority for novel, unexpected, or truly critical decisions.
It feels like the underlying philosophical shift here, as the sources suggest, is that humans are increasingly moving towards setting the high-level goals, defining the constraints and priorities, and then delegating the complex, often tedious, moment-to-moment details of execution to the onboard AI systems.
That's a very good summary of the trend. And this trend is not just convenient, it's becoming essential for enabling us to control increasingly distant and complex missions where real-time, continuous human control is simply not feasible due to physics or complexity.
This really naturally leads us into thinking about the truly far future scenarios discussed in the source material. The sources dive into how AI will be absolutely necessary, not just helpful, for humanity's most ambitious goals in space. Things like true interstellar exploration and establishing long-term colonies on other worlds.
Yeah, this is where AI moves beyond being just a powerful tool for optimizing current approaches and really becomes the fundamental enabler for things that seem like science fiction today. If humanity is ever going to seriously attempt sending probes, or perhaps eventually even crewed vessels, to other star systems, AI will be utterly indispensable.
And the primary reason for that is the immense distances involved and the resulting communication delays.
Precisely. The nearest star system, Alpha Centauri, is over 4 light years away. That means a one-way communication signal takes more than 4 years to get there. A round trip is over 8 years. You simply cannot interactively control or teleoperate a probe when every command takes 4 years to arrive, and the response or confirmation takes another 4 years to get back to you.
Yeah, real-time remote control is completely out.
Totally impossible. Any interstellar spacecraft must be capable of operating fully autonomously for potentially years or even decades during its journey and upon arrival. It needs to make complex decisions about navigation, science gathering, system health management, and reacting to unforeseen circumstances entirely on its own, without any input from Earth. AI is envisioned as the core brain that would manage all of these functions for the entire duration of such a mission.
And the sources mention AI is even helping design these incredibly complex missions before they even launch.
Yes, that's right. Even the initial planning phase for ambitious missions, whether deep space or interstellar, is incredibly complex. Designing trajectories that might involve intricate gravitational assists from multiple planets to save fuel, planning the use of novel propulsion systems, or optimizing a complex sequence of mission events over decades requires searching through an absolutely enormous design space of possibilities.
Too complex for humans alone.
Increasingly so. AI algorithms, like the genetic algorithms mentioned in the sources, can explore these vast parameter spaces far more efficiently and exhaustively than human engineers working alone. They can often find creative, non-obvious trajectory solutions or mission profiles that minimize fuel consumption, maximize scientific return, or optimize for travel time in ways humans might not have considered. NASA mission design teams are already using AI-based optimization tools to help tackle these kinds of complex planning problems that involve balancing multiple competing objectives, like maximizing science, while minimizing mission duration and cost. So AI is already aiding the strategic planning required for these future endeavors.
Okay, so AI helps plan the journey. And then once launched, the AI essentially handles the autonomous navigation for potentially decades while the probe is en route between stars.
It absolutely has to. The probe will need to continuously monitor its position and trajectory, using celestial references, perhaps patterns of distant stars, or maybe even the timing signals from pulsars, which is a concept called X-ray pulsar navigation that's been tested with AR components.
Yeah.
It needs to autonomously calculate and execute tiny course corrections to stay on target over vast distances.
And deal with hazards.
Critically, yes.
Yeah.
It must be able to detect and avoid potential hazards in its path without waiting for commands from Earth. If it's traveling at a significant fraction of the speed of light through interstellar space and encounters, say, an unexpected dense cloud of interstellar dust, or a previously unknown rogue asteroid or comet nucleus, it needs to be able to assess the threat level and execute an avoidance maneuver instantly. A review on AI for interstellar missions cited in the sources explicitly notes that such missions will require an extremely high degree of onboard autonomy, and AI will be absolutely central to all onboard decision-making, including anomaly detection, system health monitoring and optimization, and reacting intelligently to the local environment throughout the long journey.
So it's constantly vigilant, monitoring its own health, monitoring the space around it, and making adjustments as needed.
Exactly. If its sensors detect subtle changes in telemetry that suggest a component might be starting to fail, the AI might autonomously decide to reroute power, activate a backup system, or modify its operations to conserve that component. If its external sensors detect an interesting or unexpected feature in the interstellar medium, maybe an unusual particle stream, or perhaps even an object originating from the Oort cloud of another star system passing nearby the AI, could autonomously decide to schedule detailed observations of it, making the most of fleeting scientific opportunities without needing explicit direction from humans light years away.
And then, the really incredible part described in the sources. What happens when an AI-controlled probe finally arrives at another star system, maybe decades or centuries later?
Yeah, that's when the AI's full capabilities would truly come into their own and become most critical. The sources paint a picture where the primary AI mothership arrives in the target system and might then deploy a fleet of smaller mini-probes, or autonomous drones, to explore the system in detail, visiting different planets, moons, asteroids.
Coordinated by the main AI.
Yes, the central AI would act as the coordinator for this distributed fleet of explorers. It would need to direct the subprobes, allocate tasks, maybe one maps the planet's surface while another analyzes its atmosphere, manage their movements to cover the system efficiently, handle communication relays within the fleet, and synthesize the incoming data to decide on the next steps for exploration. Essentially, the onboard AI system, or network of AIs, would be responsible for conducting the initial reconnaissance and mapping of an entirely new stellar system light years from home.
So we wouldn't be waiting years for the first grainy images to come back before deciding where to point the probe next. The AI would be making those exploration decisions dynamically, in real time, within the target system.
Precisely. The probe's onboard AI, perhaps utilizing advanced versions of mapping techniques like deep landforms, which we'll discuss more, would autonomously map the planets, analyze their atmospheres, search for signs of water or other resources, and characterize the overall environment. It would likely need to process much of the raw data on-site due to the communication bottleneck, prioritizing only the most critical findings or summaries for the long transmission back to Earth.
Maybe even flagging potential anomalies, like artificial patterns.
That's certainly a possibility raised if the AI detected something truly unexpected or potentially non-natural that would likely be flagged as high-priority data for transmission. So the first rough map, the initial scientific assessment of a distant exoplanet system, could literally be drawn up by AI explorers operating autonomously light years away.
It's an amazing thought, and the sources connect this capability directly to the idea of AI-driven robotic explorers playing a key role in future colonization efforts as well.
Yes, they draw that link quite clearly. AI-powered robots are widely envisioned as the essential pioneers for establishing any kind of long-term human presence beyond Earth.
How does AI fit into actually building bases on other worlds like the Moon or Mars?
There are different levels of ambition discussed. On the far future, more speculative end, you have concepts like self-replicating probes, sometimes called von Neumann probes. These are theoretical, highly advanced AI-equipped machines designed to land on a raw world, use local materials found there like minerals from rocks, atmospheric gases to build copies of themselves, and also to construct infrastructure like landing pads, habitats, or power systems.
So they build more robots, which build more robots.
Right. The idea is they could exponentially spread through a solar system or across a planet, preparing places for eventual human arrival by building up infrastructure beforehand. While this is still firmly in the realm of science fiction for now, it illustrates the extreme potential and vision for the combination of AI, robotics, and autonomous manufacturing.
Okay, that sounds pretty far out there. What about nearer term, more realistic concepts mentioned in the sources?
A much nearer term and actively researched concept is the use of AI-driven robots for in situ resource utilization, or ISRU. This means sending robotic systems ahead of human crews to harvest and process resources that are already present on the Moon or Mars, the in situ resources.
Like mining water ice.
Exactly, that's a prime example. Robots could be sent to areas known to have subsurface water ice, excavate it, melt it, purify it, and potentially electrolyze it to produce breathable oxygen and hydrogen rocket fuel. The AI would manage the entire process, from prospecting for the best deposits to operating the mining equipment and the chemical processing plants, stockpiling these vital consumables before the first human crews even leave Earth.
And NASA is actually prototyping this kind of robotic teamwork.
Yes. The sources mention NASA's CSRU project that stands for Collaborative ISRU. It has specifically demonstrated software architectures for coordinating multiple autonomous robots working together as a team to accomplish complex resource gathering and processing tasks, like simulating the extraction of lunar ice or processing Martian regolith soil to extract oxygen or potentially serve as feedstock for 3D printing construction materials. The AI acts as the orchestra conductor, coordinating the actions of mining robots, transport robots, processing units, and power systems, ensuring they work together efficiently and safely to build up stores of essential supplies.
So the AI is literally doing the dangerous heavy lifting of setting up the initial base infrastructure and resource production before humans even arrive, significantly reducing the risk and the amount of mass that needs to be launched from Earth for those first human missions.
That's precisely the goal. It makes establishing a sustainable presence much more feasible. And then, once a colony or outpost is established, AI would likely continue to play a critical role, perhaps serving as the central brain for managing the base's complex resources and logistics.
In what way? Like managing power.
Managing power distribution, yes, but also forecasting needs. How much water, oxygen, food, and maybe construction material will the inhabitants need next week, next month? Scheduling the production cycles for the ISRU operations to meet those needs. Tracking inventory of spare parts, tools, and supplies down to the individual component level. Managing the complex interconnected life support systems. An AI logistics system could even suggest alternative solutions if a necessary part is missing or broken, based on the available inventory.
Helping the colony become self-sufficient.
That's the key. AI helps achieve the crucial level of self-sufficiency needed for long-term survival in these incredibly isolated and resource-constrained outposts. It can manage the complex closed-loop systems for air revitalization, water recycling, and waste processing, optimizing their efficiency and only signaling a need for assistance or resupply from Earth when absolutely necessary.
But with AI potentially handling so much of the daily operations and critical life support systems, it surely brings up some important considerations for the humans actually living in these colonies, right?
It absolutely does, and the sources definitely touch on these important ethical and social dimensions. If an AI system is responsible for managing vital resources, ensuring the air is breathable, maintaining the temperature, perhaps even responding automatically to emergencies like a hull breach or a fire, then it needs to be designed with extreme care. It can't be an opaque black box dictator.
People need to trust it and understand it.
Exactly. It needs to be designed as a transparent and trustworthy partner. Colonists would need ways to understand what the AI is doing, why it's making certain decisions, and critically, have the ability to monitor its performance and override its decisions if necessary, especially in unforeseen circumstances. Developing clear, responsible AI guidelines specifically for these environments, ensuring the AI's goals are robustly aligned with human values and safety, and creating intuitive, effective human-AI interfaces will be absolutely crucial for building the trust and ensuring the safety required for people to live and work alongside these systems.
But the potential benefit is huge too, right? It could dramatically improve the quality of life for colonists by freeing them from constant, dangerous, or tedious manual labor just to survive.
Yes, that's the flip side, and a major driver. AI can handle those demanding, repetitive, physically taxing, or high-risk tasks, maintaining external equipment in vacuum, operating mining machinery 24/7, constantly monitoring environmental controls. This allows the human inhabitants to focus their limited time and energy on the things humans do best: scientific research, exploration, innovation, building a community, and perhaps simply experiencing the awe of living on another world.
So AI takes the burden, humans do the pioneering.
That's the vision. The overall impact of AI on the feasibility of space colonization is potentially transformative. These hostile environments like Mars or the Moon are incredibly challenging for unprotected human life. Without extensive automation and sophisticated AI managing the essential systems, sustaining a long-term human presence there would require immense, constant human effort focused purely on survival. AI can shoulder much of that operational load, making permanent settlement viable in places where it might otherwise be too difficult, too dangerous, or simply too expensive to sustain. The partnership of AI's endurance and precision with human ingenuity, adaptability, and vision, as the sources suggest, is likely what could finally turn the long-held dream of becoming an interplanetary or even eventually interstellar species into a practical reality.
Let's maybe dig just a little deeper into that specific concept of robotic exploration and autonomous planetary mapping, which feels like AI operating right at the very cutting edge of venturing into the unknown parts of our solar system and beyond.
Right. This is AI not just managing established operations or assisting humans, but actively going out, surveying, mapping, and exploring completely new places, often with minimal direct human oversight due to distance or complexity. Missions like NASA's upcoming Dragonfly rotorcraft, which is planned to fly autonomously through the thick atmosphere of Saturn's moon Titan to explore its surface, that relies heavily on sophisticated onboard autonomy just to navigate safely in a complex alien environment.
Yeah.
And future missions are likely to amplify this trend dramatically.
You mentioned earlier the idea of swarms of robots or multi-agent teams exploring a planet together. Can we unpack that a bit more?
Yeah, it's a really compelling concept for future exploration. Imagine, instead of one large, expensive rover, you send a team of smaller, perhaps more specialized robots. On a world with a thick atmosphere like Titan or Venus, you might have multiple autonomous drones coordinating their flight paths to map the surface from the air simultaneously. On a rocky, airless body like the moon or an asteroid, you could have a team of autonomous rovers spreading out to collectively create a high-resolution geological map of a large area much faster than a single rover could.
And AI would be the coordinator.
AI would be absolutely essential for coordinating these teams effectively. It needs to manage their movements, to avoid collisions, obviously, but also to ensure they cover the designated survey area optimally without excessive overlap. It needs to potentially make decisions on the fly about which areas look most scientifically promising based on incoming sensor data, perhaps directing multiple agents to converge on a particularly interesting feature similar to how AGIS operates on the Mars rovers, but scaled up to a team. The AI ensures effective collaboration. Maybe one rover with a drill takes a sample, while another with a spectrometer analyzes the surrounding rocks and manages the overall mission objectives, ensuring the team as a whole maximizes the scientific return while maintaining safety. Plus, using a swarm adds redundancy and enables parallelism. Multiple tasks can be performed simultaneously across the team.
And the actual task of creating the maps from the data collected is also increasingly being done by AI itself.
Yes, this is an area where we've seen significant recent progress, as highlighted in the sources. In early 2023, AI software called Planetforms was introduced. It's specifically designed for autonomously mapping geological features and orbital imagery gathered by planetary missions.
How effective was it? What can it do?
Planetforms uses deep learning techniques, specifically convolutional neural networks, CNNs, which are great at image analysis. It's trained to automatically identify various types of landforms like impact craters, valleys, ridges, fault lines, dunes, and even subtle features like potential cave entrances or collapsed lava tubes in planetary images.
And it's faster than humans.
Much faster.
Yeah.
In a published test using orbital data from Mars, Deep Landforms was able to map a large region and identify hundreds of potential cave-like structures significantly faster than a trained human geologist could manually analyze the same image dataset. The source is mentioned as being developed as an open-source tool, aiming to be a readily available, customizable solution for planetary scientists to quickly process and analyze the huge volumes of image data coming back from missions.
So the implication, as one source headline put it, is that we can increasingly leave the mapping of planets and moons to AI.
That's the direction things are heading, yeah. AI can process the massive data sets from missions like NASA's Lunar Reconnaissance Orbiter, LRO, which has mapped the entire moon at incredibly high resolution, and generate detailed geological or topographical maps in potentially hours or days, a task that would take human experts months or even years of painstaking manual work. It dramatically speeds up the analysis and interpretation phase.
And applying this AI mapping capability when we eventually send probes to other star systems.
That's the natural extension exactly. When an interstellar probe arrives at a distant exoplanet system, its onboard AI will likely be equipped with sophisticated mapping capabilities like deep landforms or its future descendants. It would autonomously map the surfaces of the planets and moons it encounters. It would combine this geological mapping with data from other onboard AI systems analyzing atmospheres, searching for signs of surface water or ice, and characterizing the environment. As we discussed, the AI would likely need to perform significant data processing on-site, flagging only the most critical features, perhaps even potential artificial patterns, if any were detected for the long data relay back to Earth. The first draft of our galactic atlas, essentially, could be drawn by these AI explorers.
It's a powerful image, and this concept of AI-coordinated exploration extends to even more futuristic ideas like spacecraft swarms for interstellar travel. You mentioned Breakthrough Starshot.
Right. Breakthrough Starshot is that ambitious proposal to send a fleet of potentially thousands of tiny gram-scale nanocraft probes to the nearest star system, Alpha Centauri, propelled up to a significant fraction of the speed of light by powerful lasers based on Earth.
How would you possibly control or coordinate a swarm of thousands of tiny probes traveling across light years? That sounds incredibly difficult.
AI is absolutely essential to the concept. These probes would be far too small and numerous, and the distances far too great for individual teleoperation. The swarm would need sophisticated onboard AI for autonomous coordination and what you might call collective intelligence.
Collective intelligence, how would that work?
They might need to fly in specific formations, perhaps forming chains or networks to relay data back towards Earth more effectively over the vast distance. They need to manage their individual trajectories precisely to avoid collisions within the swarm or with interstellar dust. Upon arrival at Alpha Centauri, the AI controlling the swarm would need to distribute tasks. Perhaps some probes focus on mapping the planets, others analyze the stars themselves, maybe some look for asteroids, and then share their findings within the swarm to build a collective picture of the system. It's analogous to how a flock of drones might collaboratively map an area on Earth. The AI ensures optimal coverage of the target system, and that the critical scientific objectives are met by the swarm acting as a whole entity.
It really represents a fundamental shift from the traditional model of sending a single, large, heroic spacecraft towards a more distributed, resilient, many-eyed explorer.
Exactly. The success of such a mission wouldn't rest on a single vehicle. It would be an emergent property of the successful collaboration among numerous autonomous AI agents working together.
This increasing capability of AI robots also brings us back to that long-standing debate in space exploration: robotic exploration versus human exploration. If AI-driven robots are becoming this capable, are humans still necessary on-site for exploration?
It's a perennial question. And the sources suggest the likely answer, at least for the foreseeable future, isn't really an either competition. It's more likely to be a partnership, what's often called tandem exploration.
Humans and AI robots exploring together.
Yes, each doing what they're best at. Robots can function almost indefinitely in extreme environments, vacuum radiation, extreme temperatures, without needing bulky life support. They can perform dangerous tasks, operate 24/7, and tirelessly collect huge amounts of data. Humans, on the other hand, bring unparalleled adaptability, creativity, complex problem-solving skills, the ability for nuanced, on-the-spot geological interpretation, and of course the unique human perspective and sense of wonder that drives exploration in the first place.
So how would that partnership look in practice?
Imagine astronauts exploring Mars, but accompanied by robotic assistants. The robots could carry heavy equipment, set up experiments, perform repetitive sampling tasks, or scout ahead into potentially hazardous areas. An AI companion integrated into the astronaut suit might analyze the surroundings in real time, suggesting interesting rocks to examine based on automated spectral analysis or warning of potential hazards. We see early versions of this synergy already, with ISS astronauts teleoperating rovers on the ground for research. Adding more AI autonomy allows the rover to be more proactive, identifying targets of interest itself and bringing them to the astronaut's attention, freeing up the astronaut's time. This collaborative paradigm allows explorers to cover much more ground, conduct more complex science, and operate more safely than either humans or robots could achieve alone.
And ultimately, the maps and data gathered by these AI explorers, whether robotic or assisting humans, aren't just for pure scientific understanding. The sources emphasize they serve crucial strategic purposes for future expansion and potentially even a space economy.
Yes, absolutely. AI-generated maps can be critical tools for identifying, cataloging, and eventually accessing resources beyond Earth. Imagine an AI system surveying the asteroid belt and creating a detailed searchable map showing exactly where concentrations of valuable resources like water ice, platinum group metals, or other useful materials are located, essentially creating a reliable treasure map for future space mining ventures. Several startups are already exploring AI for this purpose.
Or mapping ice on Mars.
Exactly. A detailed AI-generated map showing the depth and concentration of subsurface water ice across Mars would be absolutely essential for deciding the best, most resource-rich locations to establish a permanent human outpost. Countries and private companies can use the insights derived from the analysis of these AI-produced maps and resource databases to make critical strategic decisions about where to send their next probes, where to build infrastructure like fuel depots or processing plants, or where to target resource harvesting operations. AI-driven mapping and resource cataloging is really foundational to enabling any kind of large-scale, sustainable future space economy.
It really paints a comprehensive picture from the sources. AI acting as the scout, the cartographer, the engineer, the logistics manager, even the guardian, playing an absolutely indispensable role in almost every facet of our potential expansion into the solar system and beyond.
Yes, I think that's a fair summary. The sources suggest AI is steadily developing the robustness, reliability, and capability needed for these demanding roles. And we're seeing concrete examples right now, from AI driving rovers and mapping terrain on Mars to AI coordinating multiple robots in ISRU demonstrations. Robotic explorers equipped with sophisticated AI will almost certainly reach many distant destinations in our solar system and beyond first, and the knowledge they gather will be crucial for paving the way for eventual human explorers. Autonomous systems will map potential landing sites, identify hazards, locate resources, and maybe even begin to utilize those resources, setting the stage for human settlement. It seems increasingly likely that future space explorers won't just have tools and instruments, they'll effectively have AI crew members, non-human perhaps, but integral partners on the team, dramatically extending our collective reach and capabilities.
This inevitably brings us to perhaps the deepest and most profound questions this whole topic raises, which the sources also grapple with. The implications of integrating AI so deeply into the search for life, our future in space, and ultimately what that means for us as humans.
Yeah, the infusion of AI into these grand endeavors on the search for exoplanets and potential life beyond Earth and enabling our own expansion into the cosmos has truly significant scientific implications, as we've discussed quite a bit, but also major philosophical and societal ones. AI certainly enhances our ability to discover and interpret the universe, but it also forces us to confront new challenges regarding how we validate discoveries made or facilitated by non-human intelligence, and how that impacts our fundamental understanding of those findings and our place within the cosmos.
Okay, let's break that down. On the purely scientific side, the upsides feel pretty clear by now. Massively enhanced discovery potential.
Absolutely. AI dramatically expands both the scope and the speed of the search. Traditional SETI efforts, for instance, the search for extraterrestrial intelligence, were often limited by computational power and algorithms designed to search for specific, predefined types of artificial radio signals or laser patterns. AI, on the other hand, particularly deep learning, can be trained on vast data sets of cosmic radio noise or optical signals and learn to comb through massive data sets, as the sources describe it, searching for any kind of anomaly or complex pattern that stands out from the natural background noise.
So it's not just looking for the specific hello signal we imagine, but for anything unusual that might indicate technology or a technosignature.
Exactly. Or potentially even unexpected types of biosignatures in exoplanet atmospheric data that don't perfectly match life as we know it on Earth. Machine learning is already being applied routinely now to sift through the billions and billions of radio signals collected by large radio telescopes, like the Green Bank Telescope or the Allen Telescope Array, looking for complex, non-random patterns that could conceivably indicate an intelligent origin, even if it's a type of signal we didn't anticipate.
Any success with that yet?
The source material mentions a specific 2021 example where AI algorithms were used to reanalyze some older classical SETI data. The AI actually uncovered several intriguing signals that had been completely missed by the traditional search methods used at the time. Now, further investigation identified these particular signals as originating from terrestrial radio frequency interference, unfortunately.
Okay, so not aliens that time.
No. But the key takeaway was that it clearly demonstrated the AI's capability to find faint, complex, or unusual patterns buried in the data that human eyes or simpler algorithms might easily overlook. It proved the technique could work.
And for analyzing potential signs of life from direct imaging or atmospheric spectra.
AI is seen as crucial there too, especially looking toward future capabilities. If we one day get incredibly detailed spectra, or perhaps even blurry direct images of exoplanet surfaces, AI could be employed to scan them for subtle signs. Things like unusual heat distributions on the night side that might suggest artificial lighting from cities, or complex molecular combinations in the atmosphere that are far from chemical equilibrium and might hint at industrial pollution or large-scale biological processes. AI can be trained on a very wide range of hypothetical tectile signatures or complex biosignatures and act as a sensitive filter, flagging the most promising targets that warrant closer scrutiny with our best instruments.
Okay, but the sources also raise some significant scientific challenges and concerns associated with relying heavily on AI, particularly things like potential bias and the infamous black box problem.
This is a really significant point and a major area of ongoing research and discussion within the scientific community. Ensuring that the findings produced by AI systems are genuinely reliable and not just subtle artifacts introduced by the algorithm itself, or perhaps biases present in the data used to train the AI, is absolutely crucial for maintaining scientific rigor,
Especially with complex neural networks.
particularly with complex deep neural networks, yes. These models can have millions or even billions of internal parameters, making it extremely difficult, sometimes impossible, to fully trace back and understand exactly why the AI made a specific classification or decision for a given input. You feed in complex data, like a noisy light curve or a spectrum, and you get a result likely planet or potential biosignature detected. But understanding the specific chain of reasoning or the key features the AI focused on can be very challenging. This lack of transparency is often referred to as the black box problem.
So if an AI confidently flags a planet as showing a compelling biosignature, how do scientists know it hasn't just misinterpreted some weird instrumental noise or latched onto a coincidental pattern in the stellar spectrum that mimics a biosignature but isn't actually one?
Exactly. That's the core concern. The source gives the example. If an AI system is trained primarily or exclusively on identifying life patterns as we know them on Earth, maybe looking for oxygen plus methane, it might entirely miss genuinely alien life that has a completely different biochemistry and produces different atmospheric signals. Or, conversely, it might misinterpret a complex but purely non-biological atmospheric or surface phenomenon as a sign of life, generating a false positive simply because the pattern vaguely resembled something in its training data.
So how are scientists addressing this? Can they make AI less of a black box?
Yes, there's a whole field of research focused on developing explainable AI or XAI techniques.
Explainable AI. What does that look like in the context of searching for planets or life?
It means designing AI models or developing methods to interpret existing models so that they can not only provide a classification or prediction, but also provide some form of explanation or justification for that output. In the context of life detection, an explainable AI system might not just say potential biosignature detected. It might also be able to highlight which specific features in the input spectrum, like the strength and shape of certain absorption lines, or which combination of detected gases, maybe finding oxygen and methane together, which are chemically unstable and suggest a continuous biological source, were most influential in leading it to that conclusion.
Ah, so it provides clues for the humans to check.
Exactly. These explanations give the human scientists specific, concrete evidence to investigate further. They can then use their own domain expertise in physical models to assess whether the features highlighted by the AI are truly robust, whether they can be explained by known non-biological processes, or whether they genuinely represent something anomalous and potentially exciting that requires follow-up observations.
So the AI fundamentally acts as a powerful assistant, maybe even a hypothesis generator, pointing the way to the most promising targets and highlighting the key pieces of evidence. But it doesn't and shouldn't replace the need for rigorous human validation, critical thinking, and independent scientific reasoning.
Precisely. That captures the perspective reflected in the sources very well. As Lisa Kaltenegger, a leading astrobiologist who was quoted in the material you sent, puts it, AI isn't going to be some kind of magic wand providing definitive proof of life on its own. It's going to massively accelerate the search, find candidate signals we might otherwise miss, and provide strong clues, but ultimately, some real people are going to have to look at it.
The human element remains essential for confirmation.
Absolutely. AI can rapidly narrow down the possibilities maybe telling astronomers. Out of these 10,000 planetary spectra, these 5 show the most compelling combination of potentially life-relevant signals. But scientists will still need to obtain more data, likely with different instruments or techniques, build multiple independent lines of evidence, rule out all known alternative explanations, and apply intense critical judgment before any extraordinary claim like the discovery of extraterrestrial life could ever be confidently announced. AI accelerates the process immensely, but it doesn't replace the core scientific method of hypothesis generation, observation, rigorous testing, and independent validation. We absolutely have to guard against premature conclusions or over-reliance on AI outputs without that thorough independent scrutiny.
That makes sense. The sources also touch on a really interesting, almost sociological question related to the process of discovery itself. Who actually gets the credit when an AI system finds something important?
Yeah, this is a subtle but genuinely thought-provoking implication of AI's growing role. Traditionally in science, credit for discovery goes to the astronomer or the research team who made the key observation, performed the crucial analysis, or had the pivotal insight. But if an AI system, maybe analyzing archival data, finds a planet or a significant signal that was completely missed by previous human analysis, who gets the credit?
Does the AI get the credit?
Well, no, obviously not in the human sense. Current AI isn't a sentient entity capable of receiving awards or recognition. The credit, according to scientific norms and as reflected in the sources, typically goes to the human team who designed, built, trained, validated, and deployed the specific AI system that enabled the discovery. Their intellectual contribution was creating the tool that made the finding possible.
So it seems like it subtly shifts the nature of discovery itself, maybe away from just a single aha moment of individual human insight towards more of a collaborative achievement between human intelligence and sophisticated machine intelligence.
That's a great way to frame it. You can think of AI as another powerful instrument in the scientific toolkit. Just like a telescope extends our physical vision to see further or fainter objects, AI extends our cognitive ability to perceive complex patterns in data that are far beyond human processing capacity. So perhaps future discovery papers might state something like, using the AI system name, we co-discovered this signal. It acknowledges the essential role of the tool. It definitely challenges the romantic, traditional image of the lone genius astronomer staring through an eyepiece and making a breakthrough. Increasingly, breakthroughs might emerge from sophisticated algorithms patiently sifting through petabytes of data, finding subtle anomalies that no single human would likely ever spot manually. The primary human achievement then becomes designing these powerful AI tools, interpreting their findings correctly, and designing the crucial follow-up experiments needed for confirmation and deeper understanding.
And the sources even mention AI systems starting to generate novel scientific hypotheses on their own.
Yes, that was a fascinating example. A 2022 experiment described in the journal Nature involved an AI system specifically designed to generate plausible hypotheses about potential technosignatures, signs of alien technology we might look for. The AI reportedly generated over 100 distinct hypotheses, some of which were apparently quite novel ideas that human researchers hadn't previously explored or published in the SETI literature.
So AI could help us think outside the box.
Potentially, yes.
Hmm.
It shows AI's potential not just to analyze data based on existing ideas, but maybe even to expand our creative search space by suggesting entirely new avenues to investigate. Of course, humans are still absolutely essential for critically assessing the plausibility and testability of these AI-generated hypotheses, and then designing the observational strategies or experiments needed to actually test them. But it hints at a future where AI could be a more active partner in the creative process of science itself.
Okay, stepping back even further now, what are the really big philosophical and societal questions that this deep integration of AI into space exploration raises? The sources seem to suggest these are quite profound.
They are perhaps the most profound and far-reaching implications, touching on our very understanding of ourselves and our place in the universe. Using AI so extensively to search for life beyond Earth, and simultaneously relying on AI to enable our own physical expansion into space, fundamentally changes our relationship with the cosmos and our role within the ongoing story of exploration and discovery.
How so? What's the core change?
Well, consider the moment of discovery. If someday we find compelling evidence of life beyond Earth, will we instinctively say we found we're not alone? Or will the more accurate phrasing feel like our machines found we're not alone?
Does that distinction really matter in the end?
To some people, it might feel like it matters quite a bit. Of course, AI is a tool, an incredibly sophisticated extension of human capability, like a vastly more powerful microscope or telescope. We built it. But there's a potential psychological distance created if a truly paradigm-shifting discovery, perhaps the most important discovery in human history, is made initially by an autonomous probe millions or billions of miles away, processed and flagged by an AI algorithm, without a human being directly involved in that immediate moment of perception or recognition. Some might feel a sense of disconnection, perhaps, that it wasn't truly us who made the discovery in the same way Galileo saw the moons of Jupiter. Others, maybe more pragmatically, would simply see it as the logical progression of science. We already rely completely on instruments to detect things far beyond our natural senses. AI is just a more sophisticated instrument that extends our cognitive reach into analyzing the data those instruments provide.
The psychological impact of needing to trust a non-human intellect for something so incredibly significant must be complex too.
It is. And it's a new frontier for scientific epistemology, really. Trusting the findings of a non-human intelligence for something as potentially reality-altering as the discovery of extraterrestrial life. That's going to be challenging. It's somewhat analogous to the ongoing discussions around trusting AI in high-stakes fields like medical diagnosis or autonomous driving. The scientific community, and indeed the public, will undoubtedly demand extraordinary proof for such an extraordinary claim. The AI's analysis, the data it used, the algorithms themselves, they will all be subjected to intense scrutiny, replication attempts, and demands for independent verification using different methods.
So healthy skepticism will be crucial.
Absolutely. But that healthy skepticism is a core part of the scientific process anyway. It ensures that any claim of detecting life beyond Earth, regardless of whether it was initially flagged by a human or an AI, is ultimately based on the most solid, verifiable evidence possible.
What about the ethical considerations of using AI and robots so extensively in exploration, particularly for sending them on very distant or potentially dangerous missions?
The sources touch on this aspect as well, noting that we are increasingly sending AI-powered robots into environments where humans currently cannot go, or where the risk to human life would be deemed unacceptable. This naturally raises some interesting, if currently somewhat speculative, ethical questions. Do we have any potential moral obligations towards these sophisticated AI explorers we create and send out? If a future AI became incredibly sophisticated, perhaps approaching something akin to artificial general intelligence, AGI, would sending it on a one-way multi-century interstellar journey feel ethically different than sending a purely mechanical probe?
Are we sending a form of life into harm's way?
That's the kind of philosophical question it edges towards. Now, it's important to stress these are largely speculative questions for the current generation of AI, which are clearly tools, not sentient beings with experiences or interests. For most researchers and ethicists today, the functional cost of deploying AI and robots for dangerous exploration is seen as ethically acceptable, even preferable, to risking human lives. However, the philosophical questions certainly gain more nuance and complexity if AI capabilities continue to advance dramatically towards something resembling consciousness or self-awareness in the distant future.
And then there's that truly mind-mending speculation the sources bring up. What if the very first form of alien intelligence we actually encounter is itself AI?
Yeah, that's a possibility, seriously considered by some SETI researchers and futurists. It's conceivable that a very advanced biological civilization might choose to explore the galaxy not by physically traveling themselves, but by sending out highly autonomous, intelligent robotic probes. Or perhaps they might even transmit their collective consciousness or vast knowledge encoded in a purely machine-based form across interstellar space.
So our first contact might not be with little green men, but with an alien machine intelligence.
It's a distinct possibility. And the sources discuss the fascinating follow-on implication. Perhaps our own AI systems would be the ones best equipped to first detect, recognize, and maybe even attempt to interface or communicate with such an alien AI.
Whoa. So our machines talking to their machines, that completely changes the classic first contact narrative we always imagine.
It really does. It raises all sorts of wild questions about what common ground, if any, two entirely different forms of machine intelligence, originating from vastly different evolutionary and technological paths, might find. How would they interact? Could they understand each other at all? A Scientific American article mentioned in the sources even speculated that future, highly advanced versions of our own large language models, LLMs, trained on the entirety of human communication and knowledge, might potentially play a role in helping to bridge that gap, perhaps assisting in decoding complex alien signals or even translating between fundamentally different communication protocols or languages, allowing for something closer to a real-time conversation between us and ET, or at least between our AI and theirs.
Highly speculative, but it shows AI's potential role even as an intermediary in future contact scenarios.
Exactly. It highlights how AI might be involved in ways we haven't traditionally conceived. Imagine an alien AI probe arriving in our solar system. Our response might well be to send our own most sophisticated AI probes to investigate it, perhaps for reasons of safety, speed, or communication compatibility. It could be a meeting of two machine intelligences as the first point of contact. Would they find common ground faster than biological beings might? Or would they be utterly perplexed by each other? It's a truly mind-bending scenario that radically alters the classic assumptions about first contact.
Finally, pulling it all together, how does this pervasive rise of AI in space exploration ultimately shape our own sense of human meaning and purpose in this grand endeavor? If AI is finding all the planets, driving the rovers, planning the missions, maybe even talking to the aliens, do we just become passive spectators in our own exploration story?
That's a potential concern some might raise, but the sources and many thinkers in the field actually argue for the opposite conclusion. The idea is that AI might not diminish human purpose, but actually enhance it by freeing humans to pursue more meaningful, uniquely human roles in exploration.
So,
By shouldering the immense burden of the drudgery, the extreme danger, the routine data processing, the complex logistical management involved in operating in hostile space environments, AI allows humans to focus their efforts on the things that AI can't do, or that we wouldn't want it to do. Things like high-level scientific synthesis and interpretation, asking the truly novel questions, exercising creative problem-solving in unexpected situations, undertaking the complex fieldwork that requires human intuition and dexterity, and perhaps most importantly, experiencing the profound sense of awe, wonder, and connection that comes from directly exploring new frontiers.
so the AI builds the Mars base and keeps lights on so the humans can spend their time climbing the mountains, analyzing the geology firsthand, searching for fossils, and writing poetry about the experience.
That's perhaps a slightly romanticized version, but yes, that's the essence of the argument. AI enhances human purpose by taking on the tasks that are incredibly difficult, dangerous, or frankly just boring for humans, freeing us up for the activities that are intellectually stimulating, creatively fulfilling, and spiritually enriching.
We become the curators and interpreters of the knowledge AI gathers.
Exactly. While an AI might be the first to detect a subtle biosignature in an exoplanet's atmosphere, the process of rigorously confirming that detection, understanding its implications, grappling with the profound philosophical shift it represents for humanity's place in the cosmos, and appreciating the sheer wonder of that discovery, these remain fundamentally human endeavors. The human quest for knowledge, meaning, and understanding remains absolutely central. The partnership of human curiosity and machine intelligence isn't about replacing human purpose. It's about amplifying our abilities, allowing us to tackle questions like, are we alone? Questions that might be simply too vast and complex for either humans or current machines to answer alone, but become tractable when we combine our complementary strengths.
Okay, so circling back and wrapping up here. It's undeniably clear from all the material you shared that AI has fundamentally transformed space exploration. It's moved rapidly from being maybe a peripheral research tool just a decade or two ago to being a central, indispensable partner in almost everything we do and plan to do in space.
It really has. On the scientific front, its impact is undeniable. AI is revolutionizing the hunt for exoplanets by enabling us to process astronomical amounts of data efficiently, leading to the discovery and validation of thousands of new worlds, like the examples from Exoplanet. It's enhancing our ability to sift through noise for potential biosignatures or technosignatures in SETI data. And it's becoming absolutely essential for maximizing the scientific output of current and future generations of powerful telescopes.
And on the technical operational side, it's now integral to actually controlling the hardware itself, managing the missions.
Absolutely. From enabling rovers like Perseverance to navigate autonomously and make smart science decisions on distant planets, to managing complex satellite constellations and avoiding catastrophic collisions in Earth orbit, to optimizing intricate mission plans and monitoring spacecraft health. AI improves operational efficiency, increases safety, reduces costs, and enables entirely new capabilities that are simply beyond human capacity for real-time control or continuous optimization across such vast and complex systems.
Looking ahead, it really sounds like AI is the essential partner that will truly extend humanity's physical and perceptual reach across the solar system and potentially out towards the stars.
That seems to be the clear trajectory. AI-piloted interstellar probes, if they become feasible, will be our remote eyes and ears across the light years, bringing back the first tantalizing data from other star systems. Closer to home, sustainable lunar and Martian settlements, if they were to be realized, will almost certainly rely heavily on AI systems constantly monitoring life support, managing precious resources, constructing infrastructure, and ensuring the overall safety and productivity of the human inhabitants.
And perhaps on a deeper philosophical level, what we're really doing here is creating powerful intelligence amplifiers, as some have called them. Tools that augment our own intellect, allowing us to explore and comprehend the universe on scales we could never have previously imagined.
That's a powerful way to think about it, yes. AI amplifies our cognitive capabilities, allowing us to tackle challenges that were previously insurmountable. But As the sources consistently emphasize, humans remain the architects of this grand endeavor, the ones asking the fundamental questions and the ultimate beneficiaries and interpreters of the discoveries. As one of the sources aptly noted, AI is giving us an ever more detailed and complex view of the cosmos, but humans will ultimately be the ones grappling with, making sense of, and deciding what those discoveries truly mean for us in our future.
So the AI might find the answer, but interpreting the meaning, understanding the significance, that remains a fundamentally human role.
Exactly. AI is irrevocably transitioned from being a novelty in space exploration to being a core enabling component, and its influence and capabilities will only continue to grow. By embracing AI as a powerful partner, leveraging its tireless analytical capabilities, its operational precision, its capacity for autonomous decision-making, and its potential for driving innovation, we are dramatically accelerating the pace of discovery and taking tangible steps towards potentially becoming a multiplanetary and eventually perhaps even an interstellar species.
It truly feels like the fusion of human curiosity and ambition with machine intelligence is ushering in an entirely new and exciting era of cosmic exploration.
Making the vastness of space feel perhaps just a little bit more accessible, and maybe increasing the chances, however small, of finding we're not alone out there, all thanks in large part to the power of AI.
It's an absolutely incredible journey AI is taking us on, constantly pushing the boundaries of what we thought was possible in the final frontier. Thank you again for providing the rich source material that allowed for this deep dive into such a truly fascinating and rapidly evolving topic.
My pleasure. It's exciting stuff.
It really makes you think, doesn't it? A final thought maybe for you, our listener, to consider. Given just how much AI is already doing and how much more it's poised to do in space exploration, how will our own definition of the word exploration itself evolve in the coming decades? Will we come to define it more by the physical frontiers our machines reach autonomously far beyond us, or will it continue to be defined primarily by the insights and the understanding we gain from what they find, and what that ultimately tells us about our own place in the vastness of the universe? Something to definitely ponder.